Good evening to all. Am I audible to everyone? Good evening to everyone. I'm Sandhya, a PhD scholar from IIT Kharagpur. Am I audible to everyone? Okay. We'll start the today's session. Before that, anyone have any questions or doubts to discuss before the session starts? Okay. As you have already seen the last week live session, which we have done, which was the first session, for the first week of the lessons, where we have covered the summary of the first week, and also we have solved few numerical questions. This week also, in addition to that, we would be discussing about the summary of second week lectures, the 5 lectures. In addition to the summary, we will be discussing few numerical questions. There will be a few questions to solve using calculator in this session, but there will be few theoretical questions which you can actually answer. Either you can type in the chat box or you can unmute yourself to answer. Let me start the session and we'll brief the last week session details very quickly, whatever you might have gone through in the week 2. If you can see, yes, please. Okay. Uh, you might have received, for example, when you open your NPTEL course session, they are uploading week 1, week 2, right? So, below that, there is one link they have provided saying problem solving session. Okay, if you click there, actually you can go to the corresponding recorded video lecture and also the PPT. You can download from there. Okay. If you could see in this slide, from lecture 6 to 9, we have studied about the strength properties of soil. If you say about strength properties of soil, for example, we have studied about the compaction characteristics of the soil. When I say compaction characteristics of the soil, the compaction characteristics of the cohesive soil and also cohesionless soil we have studied. So when I have a cohesive soil or cohesionless soil, how to determine its density, because compaction is mainly we wanted to densify the material before using, so that we can avoid the settlement of the material when it is undergoing the load application. So if you want to determine earlier, even in the laboratory, what is the moisture content to which I should actually compact my soil. So we have few methods which have been studied. One is standard Proctor test, another is the modified Proctor test. And also if you wanted to do same test on cohesionless soils like sand, definitely you will not be doing the standard or modified Proctor test. And we also have seen the behavior of dry density of cohesive soils is different from the behavior of cohesionless soils. How it is, we'll briefly discuss in the upcoming slides also. So in the laboratory, we use standard and modified Proctor test. And if you have already constructed the pavement, let us say after compacting the embankment, subgrade, everything, if you wanted to determine what is the density, and or if you wanted to confirm whether you have compacted your soil with respect to the laboratory density or not, then you have core cutter method, sand replacement method, which have been in detail discussed in the video lectures. In addition to these compaction characteristics, we also have studied about shear strength test on soil. So if I have provided some soil, either it can be cohesive or cohesionless, how to determine what is the shear strength? Why do we even need to determine the shear strength? Let us say if you have a compacted subgrade or granular layer or any of the pavement layer, Let us assume a vehicle is moving on the top of that layer. So vehicle will always produce normal stress from the top. So when you produce the normal stress from the top, each material will have its critical plane or critical direction to which it will fail. So solids will fail in certain way, liquids will fail in certain way. Even in the solid soil, different type of soils will fail in different ways. So you need to determine what is the angle or the plane to which it will fail. That is what we call failure plane or critical plane. So to determine that, we need to understand the shear strength of the soil. To determine the shear strength, we already have noted that direct shear test is one of the tests. In addition to that, triaxial test is the another test. If we understand what is triaxial test, we just need to keep that confining pressure or horizontal pressure as 0. That will be same as unconfined compressive test, because you can see in the name it is unconfined. Triaxial test is always a confined test, so if we remove the confinement, that will become unconfined. So these are the laboratory tests to determine the shear strength of the any soil. Let us say you already have constructed or you are about to construct any of the soil. So what is the main parameter? For example, if we have steel, when I have two steels, if I ask somebody what is the best steel, I have steel 1, we have steel 2. You need to have a parameter to say. Let us say elastic modulus is the parameter for the steel. In the same way, for the soils, resilient modulus. So if you want to determine that resilient modulus, you can either use the CBR test or repeated triaxial test. How do we determine the resilient modulus using CBR and repeated triaxial test is mostly based upon the empirical relations, because every time conducting a test to determine the resilient modulus, either using a triaxial test or anything, is very much cumbersome. You might not have the equipment facility every time. Then we might use a test like CBR, then use the empirical correlations to determine the resilient modulus. This resilient modulus is mainly used to design the pavement. So this is the input to design the pavement. So we need the resilient modulus test. For that we have two. Then field strength test. Let us say you already have a constructed pavement and it has been constructed over past 5 or 10 years, and you wanted to know what is the strength of that layer. So if you wanted to know the strength of the subgrade, one thing or strength of the subgrade, or sometimes what happens is when you take the subgrade, it is not only one type of soil existed there. There could be different layers of soils existed. So how do we know where the layer thickness is changing? So dynamic cone penetration test is one type of test using which we have discussed how to determine the strength of the soil or subgrade. And also in addition to the strength, we also can determine what are the variations in the layers. So all this summary which I am discussing, we will discuss in detail, not to the detail as we have discussed in the videos, but in one slide we will be discussing in further coming. In addition to that plate load test, this is also one of the field tests to determine the strength of the existing subgrade. So these are the tests which we have discussed from lecture 6 to 9. After that we have continued to the lecture 10. Sorry, somebody has joined, so I need to. So in addition to that, in the lecture 10, we have completely studied about expansive soils and their stabilization techniques. We also have studied how to determine whether the given soil is expansive or not. For that, free-swell index test is what we have studied. In addition to that, what are the types of stabilization techniques available? Why we only choose certain techniques, not everything. So these things are in detail discussed in the video lectures. So now in the upcoming 5 to 10 minutes, we'll brief all these things once. Then we'll move forward to the numerical solving questions. So as I have already discussed, when we talk about compaction which is nothing but we wanted to remove the existing air voids so that the solid particles can come together, they would be very strong. So when I wanted to do this for cohesive soils, You might have already seen this curve, which is the optimum moisture content curve. So as you keep adding the water content, initial stages, all the soil particles are very dry. Even if you wanted to apply some glues, what so initially when you try to compact it, because they are only solid particles, there is a lot of friction. You cannot compact them very easily. So then what you will do, you will start adding a little water. So that's when there will be little moisture. So they come each other very little closely, so that compaction would be a little bit easy. That is what more workable. Then you will start adding more water, further water. As we keep adding water, there comes a particular water content where this entire soil will be attaining a maximum density. That is what we are calling it as the compacted dry density or maximum dry density. Beyond that, if you still wanted to add the water, what happens? Usually, let us say now I have 1 kg of soil. So the dry density of soil, solids unit weight will be more. Now if I further add, what happens? The weight or the place which has to be supposed to be taken by the soil will be replaced by the water, because water is having little or lesser unit weight compared to the solid particles. So beyond certain point, when you add more water content, the dry unit weight will start slowly decreasing. So we do not want to add that water content, so we stop at the optimum moisture content. This is for cohesive soils. Let us say if we have cohesionless soils. Sorry, people are joining in the middle. I'm stopping to accept them. Let us see the cohesionless soil. When I say cohesionless soil, that is sand. So if you see the dry density versus water content curve for cohesionless soils, the behavior is not same. If you just observe from this, that is from the half, the behavior is same. But before that, some other phenomenon is happening. What is that? So before we discuss this, you will be seeing. Let us say if you wanted to buy some sand, so from near to beach or somewhere, usually we take one full truck of sand from there and we will be transporting to the place wherever we want. Usually people prefer that whoever actually selling the sand, they usually wanted to sell it in the early mornings, especially let us say winter and all. So when we wanted to buy that sand, the main thing is we should never buy in those conditions. Why? In the morning, let us say you go to the beach and you fill one truck of sand, you bring, you might need to travel, let us say 10 kilometers. Your home is 10 kilometers from far from the beach. By the time you come from that beach to your home, at the beach, you might see that a truck is completely filled with sand. But after traveling for 10 kilometers, it will not be. Let us say sun has already raised. So your tractor will look like empty. You might be thinking that somebody has come and taken your sand. No. You can see there is a reduction in the amount of sand. This is because of the phenomenon called bulking of sand. So what happens is, if you see the curve here, initially when there is no water content, usually only the dry soils are there. So they have some particular dry density. So after that, if you start adding little water content, very much little moisture, what happens is, we know one of the phenomenon called capillary action. This has been already discussed in brief in the video. So let me have more discussion on this. So if I add a little moisture content to this dry soil or dry sand especially, what happens? In between two sand particles, if we have a small tube kind of opening, so that creates a capillary action. Let us say when you add some water, that water is at the bottom or in between the sand particles. Due to the capillary action, atmosphere has some pressure. Below the sand, there will be some pressure. So from the bottom to the atmosphere, due to the capillary action, this water always wanted to come up, whatever the little water. So when it wants to come up, it will not allow the sand particles to be together because it always wants to move up. So this will happen only at the little moisture content. So when you keep adding more water content, let us say, when we add more water content, what happens is, so the whatever the meniscus that is formed during the capillary action. So when I say meniscus, you might be seeing that when you are studying this hydrometer, we have done a meniscus correction. So at the top there will be a meniscus formed. This meniscus usually forms only in the thin tubes. If you have a bigger pipe of 20 meters or 10 meters, you will not find this meniscus. In the same way, this capillary action also will be formed only in the thin tubes. So when we have a provision of this thinner air voids, connected air voids, that's when this capillary action will start. Water always wanted to come up. In that time, sands will be moving upwards. They will not be together. So to stop that phenomenon, what we have to do? We will be adding little more moisture. Then that moisture will go and it will break the meniscus. Then sand will start settle slowly. Then you keep adding. So initially there will be some density. Due to the capillary action, density will be decreasing. So this decrease in the density or the least density will happen around 4 to 5% of the water content. Now we will start adding further water content. That's when you can see there will be an increase in the dry density, just like in the cohesive soil. So beyond particular water content, just like in the cohesive soil, you can see there will be a reduction in the density. So this is how the little difference between the compaction characteristics of cohesive and cohesionless soils. And as far as the compaction is concerned, if we talk about soil mechanics or geotechnical engineering, there were a lot of formulas to be remembered and to solve so many problems. But as far as the payment materials is concerned, as Sir has already mentioned, there are very few to be remembered. Mainly if you know how to calculate the dry unit weight using the bulk unit weight, that is mostly sufficient. So in addition to this compaction characteristics, one of the main thing is shear strength. So for example, if you have sand, we know sand doesn't have any cohesion. So if there is any cohesion, that will be only with cohesive soils. So shear strength of the cohesive soils comes from both cohesion and also from the sigma into tan phi. So sigma is what? One of the example which has been discussed. For example, when there is a when there is a vertical pressure or vertical load from the top, it is difficult for the soil or any material to fail from the horizontal. So the vertical pressure that is being experienced by the material also plays a role in its shear strength properties. So any soil or material gets its shear strength. One is from the normal force or normal stresses that is being experiencing from the top, and also inbuilt cohesion between those particles. If you take the cohesionless soil, sand, inbuilt it doesn't have any cohesion. So the shear strength is mainly from the normal stresses. So we will not be discussing in detail about how we got and all. So these derivations have been already done in the videos. So if you have any state of the stress, if you take any material, in the material, what is the normal stress, what is the shear stress in any direction alpha. So we already have few formulas. So I am just highlighting them here because we are going to use them in the upcoming one of the problems. So in addition to this shear strength test, first one is direct shear test, which has been clearly discussed. So we have been taking some soil. So the soil will be subjected to a vertical stress from the top, and this top portion is completely fixed here. Then we will be applying a horizontal force. So what is the main purpose of doing here? First thing is we wanted to determine what is the shear strength of this material. So now we have some material. What is the shear strength of this material when it is subjected to some vertical load? Here let us say this vertical load is some vehicle load coming from top. So this vehicle load is coming from top is, let us say, some sigma kilonewtons. Then what is the horizontal force required so that my soil material can be failed? That corresponding horizontal force we need to determine. So what will I do after determining that? Let us say sigma 1 is the vertical force I have applied. Then I will determine the corresponding tau 1, which is the shear stress. And again I have applied sigma 2, another normal force. Then I have determined what is the second horizontal stress that is being taken by the soil, that is tau 2. So if we have let us say two equations like this, what are the unknowns here? You know the applied stress, you know the tau 1. Then in two equations, unknowns are C and phi. So cohesion and angle of internal friction. These are the two main properties of the soil. So if we know these two properties, cohesion and angle of internal friction, we can actually have a basic idea about any of the soils. If you have 2 to 3 soils, having higher cohesion, you can tell that they have higher shear strength. Having more angle of internal friction, you can still tell that what is the property of that. So this is how these two are basically required. So direct shear test, using this, we can actually determine C and phi. So what is the disadvantage of this? Because if we already have one test like this, why do we need to go for another test? So there are few advantages and also disadvantages. One of the main disadvantage is, for example, here I have a particular amount of material. I am trying to shear this material from horizontally exactly at the half. So I am allowing the material to fail at this plane. That means I am already defining, I am already indicating that my material should be failed. My material should be failed in this horizontal direction only. But in reality, it will not be the case. When a wheel load is coming from top, it can be any direction, the material can be failed. It can be with any angle. So there is no provision here to understand where exactly is the material's failure plane is. That is one of the major disadvantage. So by including that disadvantage and improving, so we have triaxial test. Here in the triaxial test, we already know we have a specimen. We try to apply surrounding confining pressure to the specimen. Then we try to apply the different deviatic stresses or vertical stresses. So when I keep the confining pressure as constant, and when I keep changing this deviatic stress, how the specimen thickness is going to change. That is what we are going to determine using some dial gauges. So there might be two stages. So in the first stage, we will be applying this confining pressures laterally. In the second stage, we will try to apply the vertical stress as sigma D or deviatic stress. And in each two stages, so if I allow the whatever the water existed in between the soil, if I allow from bottom, let us say, by opening some outlet or pipe, then what happens? We are allowing the specimens to compress. We are allowing the specimens to consolidate. So those are called consolidated or drained states. So in the second case also, let us say when I applied this deviatic stress or vertical stress, if I allow that drainage, that is what called drain test. So we already have three different tests which I am not going to discuss here in detail. In the stage 1 and stage 2, based upon the type of drainage condition we are providing. So what is the main advantage of doing this triaxial test is, if you see here, this sigma 3 and the sigma d which is applied from top, both of them are perpendicular to particular planes. Sigma 3 is perpendicular to this length. Sigma d will be perpendicular to this top. That means we are only applying the normal stresses here. We are not applying any horizontal stress like in direct shear test. So whenever there are only normal stresses and there is no shear stress, those planes are called as principal planes. So what is the advantage of that? Previously we already have an equation to calculate the normal stress and shear stress on any plane. So let us say if I have a sigma equation here, now I understood that the sigma 3 is the only force that is being applied on this plane. That means there is no shear stress. Then we can consider this sigma x as the sigma 3. And if you already have a deviatic stress from top, usually we call that as sigma y. But here that sigma y equal to sigma 1 you can call, because there is no horizontal shear stress that is being applied on the specimen. So directly here you can actually substitute, instead of sigma x and sigma y, sigma 1 and sigma 3 you can substitute as I have shown here. And in this equation, if you see, I already removed this last tau xy term, because shear stresses that whatever that is being applied are already 0. So by having these simplified formulas, it will be very easy. It will be very easy for what? Our final aim is, for a given soil specimen, we need to determine what is the cohesion C, what is the angle of internal friction. If you know the cohesion and angle of internal friction, you can determine the shear strength particular to that angle of friction or particular to that failure plane. So this is the main aim. The calculations and determinations will be easy compared to the direct shear test, because here we are assuming that whatever the planes are principal planes. So in the given triaxial test, if I don't have any confined pressure, sigma 3 here, sigma 3 is 0, and if you have only the vertical stresses, we call that as unconfined compressive strength. And if you see here, this is the repeated triaxial for pavement analysis. So the same triaxial test, so in the field usually the load is not static. Vehicles will be always moving. So you can't simply keep a vehicle in static for 10 minutes and immediately take the load reading. So we need to repeatedly apply the load and see how the material is behaving. The advantage of that is, by applying the repeated loads, we can determine what is the plastic strain, what is the recoverable strain, so that we can calculate the resilient modulus. Using this resilient modulus, we can actually do pavement analysis and design, because this resilient modulus will be input for the subgrade modulus. So in addition to that, as we have already summarized, CBR, dynamic cone penetration test and plate load test. This CBR is for laboratory strength determination of soils, whereas dynamic cone penetration test and plate load test, these two are for field determination. So we already know in the California bearing ratio test, we already have, let us say, soil specimen. We take a plunger, we will try to apply the load onto the soil specimen. So when we apply the load onto the soil specimen, we will be noting down the deformation or change in deformation. Change in deformation of the soil specimen. So when the deformation reaches to 2.5 mm, here we are applying some load, then we are observing the deformation. So corresponding to the 2.5 mm deformation, what is the load that I have applied, and corresponding to the 5 mm deformation, what is the load that I have applied, we will be taking those proving ring readings. By using that, so we already have the standard crushed aggregate which have been actually done in California. They have a particular load reading, proving ring reading corresponding to the 2.5 mm and also 5 mm. So we will compare our material strength with respect to the standard material strength, and we will be reporting them as the California bearing ratio values in terms of percentages. So always the CBR value at 2.5 and 5 mm will be noting down. Then if we come to the CBR graph, if when you have done the CBR, you can get your graph either in the one which is shown in the top or in the one which is shown in the bottom. So most of the times you must have seen If your curve is like the one which is shown in the bottom, you need to do the correction. But why do you need to do the correction? What makes you to do the correction? Reason is, for example, when you see the top curve, which is a convex curve, there is no sudden change in the curvature of the curve. But you can still observe a change in the curvature, and after 2.5, let us say, the movement will be same. But below that, it was different. That is concave. It actually indicates that initially when we start applying the load from plunger to the soil, we will be applying some seating load, right? So we give that seating load in order to make sure that there is a proper contact between the soil and the plunger, so that immediately when I start applying the load, it will not be an impact. So whenever still after doing giving the seating load and applying the load with a particular per minute rate also, sometimes it can happen that the initial concave portion says that there was a rapid application of load compared to the one which you are supposed to give. So whenever you have this concave portion, which shows that whenever the load is applied through the plunger, so initial starting times, the load application was very much rapid. Then you might need to take a tangent from this curve. From there, for example, from 0, here this is the tangent touching here, the red laser point. So this is the shift. Usually the reading must have started here, but it has started early because the equipment has given the application of load a bit in rapid manner. So for CBR, we need to observe this and do the correction. And this CBR values minimum requirements changes for subgrade and subbase materials according to the application. And when it comes to the plate load test, so this is one of the field tests where we have a standard plate which is placed on the subgrade, and dial gauge will be attached to here. Using the hydraulic jack, we will be applying the load and we will be determining what is the change in the deflection. So based on that you can, so here there is a pressure gauge. When this plate undergoes the deformation of, let us say, 1.25 mm, what is the corresponding pressure? That is what your aim here. So if you know that pressure, we know the deflection for which we are taking is 1.25 mm, then the ratio will be the subgrade reaction. Mostly the subgrade reaction can be used to determine the strength of the subgrade layers. And this also will be used in concrete pavements for other purpose, but here mostly we are trying to use to understand the strength of the subgrade. And if you take the dynamic cone penetration test, as I was discussing previously, one of the main reason you know that, for example, this is the hammer weight. From particular height, this hammer weight will be released from top to bottom. Then what happens? Whatever the cone at the bottom, that will start entering into the subgrade or soil. So whatever the amount of or deflection that has been penetrated into the soil will be noted. So that for each blow. How many blows are required to take, let us say, 1 those readings are fine. In addition to that, what happens? Let us say you have started here, x-axis, let us say there are number of blows. At 0 blows, your cone is here. As you keep increasing your blows, your penetration of the cone is moving forward, moving forward, moving forward. After particular amount of blows, again when you start increasing your blows, you observed a change in the slope. You can see till this is one slope, till that is another slope, which indicates that there is a change in the soil layer. Till this it might be a black cotton soil, and beyond that it could be a red soil, or beyond that it could be a hard rock or something. So if you want to determine where actually the stratas are changing, most of the time people do use this dynamic cone penetration test. So let us solve few numerical solutions. And anybody have any questions till now? Till now for water we have discussed Anyone needs any other clarifications, or can we proceed with the numericals? Okay, let me proceed. So this is your first and easiest question. For conducting the light compaction test, so when I say light compaction and heavy compaction, mostly the difference would be weight of the hammer is different, the fall of the hammer is different, the number of blows per layer we are giving is different, and also how many number of layers we are compacting is different. So you can see the options A, B, C, D. Maybe you can, even if you don't remember all the height of fall and all, you can still make a guess. So what is the option for light compaction? You can either type in chat box also. Based on hammer weight, you can still tell. Anyone? Yes, the option D. Dinesh says option D with 2.6 and 310 25.3 is for light compaction. So we use 2.6 kgs of hammer, and fall of hammer is 310 mm, 25 blows for each layer, and we compact in the 3 layers. And if you come to the second question, on the left side I have given all types of rollers to compact the soil in the field. On the right side I have given the type of soil. So now you need to determine which type of roller is suitable for which type of soil. If you see the ABCD options, let us say you did not remember which is useful for which type of soil. Let us eliminate by starting with whatever we know. We know vibratory roller. I think most of the people might be knowing vibratory roller will be used for what. So vibratory roller will be mostly used for at our homes also when we have sand or cohesionless soils. Usually we put the vibratory roller, so it will be vibrating and compacting by itself. So we know D is for 3. Vibratory roller is for cohesionless soils. And so when it comes to the pneumatic roller, smooth wheel roller and sheep foot roller. Let me start with sheep foot roller, because for me that is a little bit easy compared to these two. So sheep foot roller, if you see here, I know that this is used for some cohesive soil. But if you come to the right side, there are options cohesive and granular layer, option 1. Second is plastic soils of moderate cohesion. Fourth is silty soils of low plasticity. So I wanted to eliminate the fourth option, silty soils of low plasticity, because they are already saying it is a silty soil. That means which is not a clay, and they have low plasticity. That means that is also not cohesive, much cohesive. So it is not fourth option. Third is already eliminated. So out of 1 and 2, cohesive and granular, plastic soils of moderate cohesion. Sheep foot roller is used for either 1 or 2. Anyone? Any guess? Sheep foot roller is either for 1 or 2. One is cohesive and granular. 2 is cohesive with moderate plasticity. Yes, Shantanu says 2. Okay. Okay then. We also have eliminated this. Sheep foot roller is for plastic soils of moderate cohesion. Then we are left with pneumatic roller, smooth wheel roller. So pneumatic rollers are usually used for the soils which are of low plasticity. Then whatever is left, you can actually guess. Okay, you can see the answer here. Pneumatic rollers are used for silty soils of low plasticity. And these smooth wheel rollers are used for both cohesive and granular layers. In upcoming slides, I will also ask one of the question. For example, when I choose sheep foot roller for plastics also moderate cohesion, why? Why only sheep foot rollers? So that would be one of the question. So currently this is the answer for this question. So coming to the third question, half of the question is very easy, but another half, let us see how we will be able to proceed. So in the laboratory compaction test, the optimum moisture content of soil decreases. So for example, I have a optimum moisture content for the given soil. I wanted to decrease the optimum moisture content of that soil. So if any time if you want to reduce the optimum moisture content of any soil, what you need to do? Option A says with increase of compaction energy and with decrease of coarse grains in the soil. So with increase of compaction energy, I think I am confident about that, because if my soil gets compacted in 25 blows, I have OMC 1. If I give more blows, definitely my OMC will be less. It will be attaining very quickly. So with increase of compaction energy, so option A and C has with increase of compaction energy. So I can eliminate B and D. So out of A and C, there is second part. In addition to the increase of compaction energy, option A says that with the decrease of coarse grains in the soil, and option C says that with the increase of coarse grains in the soil. So which option do you people think is the correct? So in the given soil, if I increase the more coarse particles, will the OMC will be decreased? Or if I decrease the coarse grain particles in the soil, will the OMC decrease? Is it option A or C? Yes, it is option C. Why? Whenever there is more fine particles, because of the higher surface area, it always wants more amount of water to reach into the optimum moisture content state. So whenever you try to replace the fine content with the coarse content, definitely the OMC will be reduced. So the option is C. And coming to the fourth question. Why sheep foot rollers are more effective in compacting clayey soils? So previously also in one of the question we have selected this. Why sheep foot rollers are effective? Option A says there is a differential expulsion of water under the roller. So they are telling that when the roller is moving over the soil, some amount of water will come out expulsed. So because of that, it is getting compacted better, they are saying. Option B, contact pressure is high. So because of higher pressure, higher compaction is happening, they are telling. And option C, roller speed is high. Option D, drum width is large. So let me eliminate the easiest one. Roller speed is high. So if any vehicle is moving with high speed, what happens? If I am moving with 60 kmph, what happens? The time of contact between the bottom of the wheel and the road will be very less. So if I place a roller at particular place for 1 hour, there will be more settlement. If the roller just passes very quickly with 50-60 kmph, there will not be much contact, there will not be much load contact, so the compaction will not be better. So roller speed is high, because of that we are having effective compaction is wrong. So C is wrong. Drum width is large, because let us assume all the drums are of same width I am talking about. So D is also I am eliminating. So out of option A and B, which option do you people think is the correct reason or appropriate reason for effective compacting clay soils? Is it because of the expulsion of water, or is it because the contact pressure is high? Yes, option B, correct. Because contact pressure is high. Because if you take the option A, there is a differential expulsion of water. Usually we are adding the water to the soil so that it will act as a lubricant, then it will make the soil to be more workable to compact. Here our purpose is not to remove any of the existing water from the soil. So expulsion of water is a wrong option. So contact pressure is high. Whenever there is a more contact pressure, whenever there is more loading time, then we can observe, because we are transferring more compactive energy from the roller to the soil. So that is the reason why sheep foot rollers are more effective. So there is a numerical problem. A sample of dry sand tested in triaxial and direct shear test. In triaxial test, the sample fails. So they have taken the sand. So whenever they are giving type of soil, please note down. When they are saying dry sand, what does that mean? What is the cohesion of dry sand? So indirectly they are giving the C value also. So dry sand cohesion is 0. And they have tested the sand both in triaxial and direct shear test. And in triaxial test, sample has failed. When it failed is when the major and minor principal stresses are. Major principal stress will be sigma 1, minor principal stress will be sigma 3. Those two values are given. So in the triaxial, if my sand has failed with the sigma 3 and sigma 1, what will be the shear strength in the direct shear test? So if I take the same sand and test the specimen in direct shear test, so I tried to apply a 230 kilonewton per meter square from the top. So what is that horizontal shear stress I need to apply so that my sand will be failed in direct shear test also? So see here, dry sand they have mentioned, that means cohesion is 0. Sigma 1 they have given 960 kilonewton per meter square. Sigma 3 is given 260. So they are asking us to determine the shear strength of the sand. So to determine the shear strength, what is the formula? Tau equal to C plus sigma tan phi. Here C you don't need because C is already 0. Sigma tan phi. Sigma is vertical stress. They have already provided normal stress or vertical stress is 230 kilonewton per meter square. So what is unknown here? Phi. So if you could able to determine the angle of internal friction, we can calculate the shear strength. So what everything I have is sigma 1 and sigma 3. Now we need a correlation between sigma 1, sigma 3 and phi from the triaxial data so that I can solve this problem. So in one of the video you could have seen this equation, sigma 1 equal to sigma 3 into tan square 45 plus pi by 2 plus 2c into square root of tan square plus 45 plus pi by 2. So because this is a sandy soil, cohesion is already 0. So you can keep C as 0. So sigma 1 is given, sigma 3 is given, only phi is unknown, and if you calculate phi value you will get. If you want you can do now also, otherwise it is just a substitution. You will get phi value as 35.01 degrees. So if you know the phi, it is directly substituting tau equal to sigma is 230 into tan 35.01. So shear strength you will get 161.11 kilonewton per meter square. Is there any doubt in this question? I think this is a very basic and easy question. Everything is given mostly. Okay, those questions actually in the NPTEL section where you are actually receiving your assignment left side, below that they have added some extra section saying problem solving session. If you click there, they have provided the links for both Monday and Tuesday problem solving sessions and also for the material to download. So you can download from there. Okay, if everybody is clear with this question, let us move with the next question. Okay. The moisture content corresponding to highest shear strength in the soil is usually dash than to the moisture content at which dry density is maximum. Maybe you can read this question to understand another time. So if you take the optimum moisture curve, now we have two things. One is maximum dry density, one is maximum shear strength. So whatever the OMC curve that we are actually preparing using Proctor test is for maximum dry density. It is not for maximum shear strength. Okay. The OMC is corresponding to the maximum dry density. It is not for maximum shear strength. In the field, this shear strength can be changing with any time. Let us say, if I have a vehicle with 10 tons moving on the top, that is, let us say, normal stress. The amount of shear stresses produced by the material will be different. And if I keep changing the normal stresses, my shear stresses would be changing. So the shear stress or shear strength will be, shear stresses will be keep on changing. And if you take the dry density, so we will be taking the worst condition, let us say soaked severe, and we assume that there will not be any further worst condition in the field. So we will be compacting the all the layers into the optimum density. So the OMC curve, whatever you are seeing is actually for maximum dry density. This is not the shear strength. So now the question is, let us say OMC is in the middle, optimum dry density. If I want maximum shear strength, will my OMC be lower than the maximum dry density or higher? I will explain the reason why, but I wanted one of you to type in the chat box. If I have a OMC in the middle, let us say after maximum dry density, for the same soil, if I want to compact for maximum shear strength, will the water content will be less than OMC or more than OMC? When I say less than OMC, that is dry side of optimum OMC. When I say more than OMC, that will be wet side of optimum. So, yes, option, he says option A. This is lower side. Why? Because if you take the OMC curve, optimum dry density curve, initially when you try to add the moisture content slowly, before OMC, all the soil particles are flocculated in state. Like they are they are about to come into the compacted state. Beyond OMC, what happens? They all will be dispersed. They will be arranged in the flat structure kind in layers. So the shear strength will be maximum only when they are like well graded state, or you can say they are in completely flocculated state. So anytime if we want to compact the soil for higher shear strength, it is always on dry side, which is nothing but the lower water content on the OMC. And this question, specifications on minimum field density of subgrade layer in pavement construction is based on. So if you could have seen in one of the video, it was mentioned that I have also mentioned in one of the table. For subgrade, you have a different criteria to compact, because we are not going to compact subgrade to the maximum dry density and also subbase and base, because if you move from top to bottom of the pavement layers, top is the most priority one, because that is being subjected to the more critical stresses from the wheel loads. As you move from top to bottom, the importance decreases, because the stress distribution will be distributed to more contact area. So we try to use the cheap materials at the bottom, but more effective materials at the top. So if you consider the subgrade layer, there was a specification that minimum this much field density should be achieved, minimum 97%, 98%. So this is based upon which test? Whether it is, this is not based upon C. It is not based upon the test methods and NMAS. You also know this is not based upon test methods, depends upon design traffic. It must be either standard Proctor or modified Proctor. Which is more relevant, do you think? A or B? So modified Proctor test is the more relevant one. So I have kept the snip here. For embankment, we have a criteria that at least 95% of whatever the lab density you are expecting, at least 95% of that of modified Proctor density. And if you take the subgrade, 97% of modified Proctor density. And if you take the subbase and base, it should be greater than or equal to the 98% of maximum drive density. So if you take the next question, in pavement engineering, plate load test is used to estimate. Why do you need to do the plate load test? Let's start from the first. Dry density of soil for analysis of concrete pavement. They are saying that for concrete pavements, if you want to determine the dry density, we need to do the plate load test. So when we did the plate load test, anytime did you determine any dry density? We already have core cutter and sand replacement methods for determining the dry density of subgrade soils. So obviously must not be a CBR value for analysis of flexible pavement. Okay, I don't know whether this is correct or not because we are doing this plate load test for subgrade. CBR is somewhere related to that. Let us move further. Modulus of subgrade reaction for analysis of concrete pavement. D. Resilient modulus for analysis of concrete pavement. Which option do you people think? Yes. So usually we do this test to determine the modulus of subgrade reaction for analysis of concrete pavement. So corresponding to the 1.25 mm of deflection, what is the pressure that needs to be applied is what the ratio gives the modulus of subgrade reaction. And now, dynamic cone penetration test can be used for estimating option A, compressive strength of concrete pavement. Do we use the dynamic cone penetration test for compressive strength determination, or thickness of layers in flexible pavement, or in situ CBR of subgrade soil, in situ dry density of soil? So what is the most appropriate answer? Dynamic cone penetration test. So which option do you all think is correct? Dinesh says D, thickness of layers. So this is another one of the purposes, change in the strata. Okay, in addition to that, what is the main purpose of DCP? If you people remember, there was an empirical correlation using DCP value. So usually where do we perform this DCP? Do we directly perform on the top or do we perform on subgrade only? Anyone? Ravi says option C. Okay, let us see which is the correct option. So, okay. So usually this DCP, do we perform only on subgrade? In the video, once sir has discussed that, let us say if the subgrade is not available for the test, then we will be making a pit. We will be trenching at one place. We will make sure that subgrade is exposed. Then we will place our DCP upon that subgrade and we will test. So that at the end we will be determining the CBR of that subgrade soil, because this is the field test for CBR. And as far as option B is concerned, thickness of layers in flexible pavement. Usually thickness of layers in subgrade, if they have mentioned, that could have been the option. Because within the subgrade soil, when you will be definitely starting the test on subgrade surface. So beyond subgrade, if there are changes in the thickness of the layers, if there is any change in the strata, that is what we can determine using DCP. But thickness of layers in flexible pavements you cannot. Okay. Okay, we are almost to the end of the session. We have some few last questions. Okay. The 10th question is, a repeated triaxial test was carried out on a cylindrical soil sample having 100 mm dia and 200 mm height. Okay. The confining pressure, deviatic stress and recoverable deformation obtained during the experiment is shown below. Calculate the resident modulus and stress invariance. So if you can see the data given here, they have mentioned the dimensions. You can see 100 by 200 mm is the specimen. In the 100 by 200 mm specimen, for this confining pressure, let us say, they have started testing with the different deviatic stresses and they have started observing the recoverable deformation in each stage. They are asking to determine resident modulus and also stress invariance. How do we do? Any idea? How do we usually calculate the resident modulus? Okay, using CBR, but here CBR is not given. What we have been given is only triaxial data. So we have recoverable deformation, we have deviatic stress. So using this, can we determine the resident modulus? So usually elastic modulus is stress by strain. In the same way, resident modulus will be stress by strain. But which stress we have to use? Because we have confining stress, we also have deviatic stress. So we will be using the deviatic stress. So we already have the stress, sigma d is here, recoverable deformation is here. If you take the ratio of these two, we will be getting one is resident modulus. So, okay, we can calculate resident modulus. And another thing is stress invariance. Anybody remember how to calculate the stress invariance? You have confining pressure, you have deviatic stress. Is there any way we can calculate the deviatic stress? Stress invariant is, if you could have remembered, theta. Anyone, how to calculate the stress invariant if you have deviatic stress and also confining pressure? Any guesses? Okay. If we have deviatic stress and if you have the confining stress, if you have these two, we can actually calculate the sigma 1. That is the major stress. How it will be calculated? Confining stress sigma 3 plus deviatic stress sigma d is equal to the sigma 1. So usually stress invariant is the summation of all principal stresses. When I say principal stresses, sigma 1 plus sigma 2 plus sigma 3. Sigma 3 is directly given. Sigma 1 you can calculate, sigma d plus sigma 3. But how do we get the sigma 2? So here we assume that sigma 2 equal to sigma 3. So if we know these two, definitely we can calculate the stress invariant. So for one of the row I have calculated, you can see here. Sigma 3 is given, sigma d is given, recoverable deformation is given. So first you have to calculate recoverable strain. How do we calculate the strain? Strain equal to recoverable deformation by original length of the specimen height. Specimen height is given as 200. So recoverable strain we have calculated. If you know the strain, how to calculate the modulus? Modulus is always stress by strain. But which stress? Deviatic stress. 6.894 divided by which strain? Recoverable strain. Then if you take the ratio, you will get the resident modulus. And if you want to calculate the stress invariant theta, which is nothing but sum of sigma 1 plus sigma 2 plus sigma 3. Sigma 3 is already given directly. Sigma 1 you can calculate. Sigma 1 will be sigma 3 plus sigma d. So 137.88 plus 6.894. and sigma 2 value will be equal to sigma 3. So if you sum up these three, you will get the stress invariance. You can proceed doing this for remaining things. This is the simplest question I have given, but still this question actually if you still wanted to further try, so this is how it will be for remaining. So if you still wanted to extend this question or if you wanted to try in your free time, we have some models. For example, resilient modulus is a function of k theta parameters. So there are few models to determine the resilient modulus of soil. So if you take any of the model, from the previous problem, you already know the resilient modulus. PI is the atmospheric pressure. Sigma D is the deviatric stress. PI is again atmospheric pressure. Theta is the stress invariance. So what are the unknown parameters here? K1, K2, K3. These are called as K theta modal parameters. So you can actually determine these parameters. Like anybody can ask you to determine these parameters. So if you take this equation, most of the things are known to you, but only K1, K2, K3 are unknown. So if you have three unknowns, if you could able to write three equations, you would be able to solve them and find out those K1, K2, K3. So is there anybody having doubt with this? Okay, I assume everybody understood. Let us take another question. Maybe you can solve this using your calculator. Triaxial test was done on a soil sample by varying the confining pressure and deviatric stress. So in the triaxial test, these are the confining pressure sigma 3. First they have taken 25 as sigma 3, then they have applied 50 deviatric stress. Then they have observed what is the change in the height of the specimen or recoverable strain. Then they have changed the confining pressure and observed the different deviatric stress. They have done this trials for 3 sets. Using this data, calculate the value of cohesion C and phi of the soil. So sigma 1 and sigma 3 and sigma D is given. You have to calculate C and phi. So this is a correlation which I have already mentioned. Sigma 1 equal to sigma 3 into. Okay, this is the correlation. You can note down this equation. Sorry. So in this equation, from the first row, sigma 3 is known, sigma D is known. You can calculate the sigma 1. So you can substitute sigma 1, sigma 3, then 5, C are the unknowns. So one equation you will get. So you can see here. So if you take the first equation, you can substitute sigma D and then you can calculate the sigma 1. If you substitute everything, in the first equation the unknowns are cohesion and phi, C and phi. In the second equation also C and phi. So because unknowns are two equations are enough to solve this. You will be getting C and phi as this. Anybody have any doubt in this question? Okay. Okay. Let us see that last chapter, which is expansive soils chapter. I have 2-3 questions. I think people can answer this. These are very easy questions. So one of the concept you could have remembered is diffuse double layer. So because of this diffuse double layer, you can see around the clay particles there is a strong and weak bonds of water will be presented. So because of which some type of soils have the ability to hold the water and they try to improve their or expand their volume. These soils we call as expansive soils. So our main aim is what? To determine or to prevent this expansion, we have to add some external material so that instead of water coming and forming this double layer around the soil, we are adding something external like lime so that the cations or whatever the polars or non-polars will come and contact with the clay, they will form the stronger bond and improve the strength of the clay also. That way we can actually eliminate the formation of diffuse double layer and improve the strength of the soil. So the question is, diffuse double layer in expansive soil indicates. What does it indicate? The option A says formation of rigid and loose layer of water molecules between the clay particles. So they are saying there is one layer with rigid and loose. So one is strongest layer, one is the loosest layer of water molecules between the clay particles. Option B is tetrahedral and octahedral layers of silicon and aluminate groups in clay particles. So does this tetrahedral and octahedral layers implies diffuse double layer? Is that correct? And option C is formation of oxides in wetted clay soils. So when I say wetted clay soils, what? So this is one of the way of preventing the expansion. So before actually using the soil for the construction, we wet the soil, we pre-wet the soil so that we make the soil into the saturation stage. That is what wetting the clay. And the fourth option is adsorption of water on the surface of clay particles. So which option do you all think is correct? You can have a look at once. When I say diffuse double layer, is it only the adsorption of water on the surface of the clay particles or the formation of oxides, or are they the tetrahedral and octahedral? You can even guess also. He says option D. Okay. Is there any other options? Any other guesses? If you want to see the options, you can see. Okay. If there are no options. So we know that clay has on the surface the negative charge, on the sides it will have positive charge. So on the sides positive, on the surface negative. When it has the negative on the surface, it tries to attract the positives. So we wanted to actually, usually what happens, water will come, the H plus ions will come and form a rigid and loose layer of water molecules between the clay particles, because of which we are actually calling this as diffuse double layer. There are two layers. One layer is especially of rigid, another is loose. So you can actually get rid of the loose as you move from surface of clay to the far away, the strength of the layer will be very loosen in structure. So from rigid to loose. So slowly we add the lime so that this rigid loose layers, instead of water, we make either lime, any cations within the lime or any external material, make that rigid layer instead of water. So this diffuse double layer is usually due to the formation of rigid and loose layers of water molecules between the clay particles. So we wanted to avoid this replacing these water molecules with any other cationic or other molecules, so that they in turn should also improve the strength of the soil, not just eliminate the diffuse double layer. Okay. And this question, during the cation exchange in the stabilization process of expansive soil using the lime. So when I use the lime is nothing but CaO, calcium oxide. So when I add the calcium oxide, it was option A. Okay. 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 For the question 13, we have almost finished. We just have 2-3 slides. So we'll finish quickly. So during the cation exchange, so I have a lime, calcium oxide. So when this calcium oxide added with the clay or water, what happens? Ca plus 2 is cationic and O, they will be separated. They are asking that, so this Ca plus 2 will go and replace with something, or actually strengthens the bond of soil by replacing what? Let us say option A is this stabilization process of expansive soil using lime. During the cation exchange, silica and alumina reacts with the lime hydrate to form the shear gel. You see, individual sentence might be true. You have to understand whether this sentence has anything to do with the cation exchange of lime or not. Okay. Your option says silica and aluminum, when they react with lime hydrate, they form the shear gel. And the second option, so is there anywhere this cation exchange is happening in the formation? If not, then option B is moisture content in the soil decreases. So they are saying that because you are adding Ca plus 2, this is going and replacing with something else, so that moisture content is decreasing. Option C is OH ions dissociates silicon and alumina present in soil. Okay. Then option D is this calcium plus 2 replaces the monovalent ions in the soil. Any guesses? Okay. Ravi says option A. Option A, silica and alumina reacts with lime hydrate. Individually sentence is correct. Okay. Any other guesses? Okay. Everybody mostly says option A. Option A individually is correct actually. It forms CSH gel, but it is not forming in the cation exchange. So if you could have seen the process of lime exchange, there is initial process, and the second stage there is something called pulverization. So pulverization is the stage where all these calcium silicate hydrate gels will form and soil becomes completely strong. So before even soil becomes strong, before that the process is cation exchange, where this calcium plus 2 ions will come and they will replace the soil ions. When I say soil ions, on the top of the soil, whatever is existing in, for example, on the top of the soil, negative charge will be there. These negative charges actually attracted with the monovalent ions of soil, water, moisture available. But the Ca2 plus first will come and replace. After replacing that, only you are going to get any of this further process. So this is stage 2. Pulverization, during which CSH gels will form, will be the second stage. But initial stages, this calcium plus 2 ions replaces the monovalent ions in the soil. Okay, in continuation to that, let us say if I have a soil and if it has more diffused double layer. When I say more diffused double layer, is it a weak soil or not? It is obviously a weak soil, because more diffused double layer means more amount of expansion. So we wanted to avoid that. So here the question is, the plasticity characteristics of clays are due to its option A. So if I have a clay, I have plasticity to the clay because of what? Is it because of the adsorbed water? Is it because of the free water? Is it because of the capillary water, or none of the above? Any guesses? Is it adsorbed, free, capillary, or none? So every time whenever we are determining the plasticity index, so that plasticity index value of each soil is because of what? Ravi says option C. Okay, he says due to the capillary. Any other guesses? Usually the plasticity of soil is it due to the adsorbed water? So when I say adsorbed water, adsorption means this is a surface phenomenon. Absorption is a material phenomenon. So if I have a clay particle, clay surface has negative charge. So if any water comes and H plus ion from that water gets attached to the clay, what happens? All the water molecules are placed on the surface of the clay. That phenomenon is called adsorption. So they are saying, so this plasticity, is it because of that adsorption or free water? So when I say free water, if you take the clay, around the clay, so much water has come and absorbed. That means it has come and attached to the clay. Beyond that, if you move away from the clay particle, still there is some water available in the soil, but that water or moisture content is not exactly attached to the clay. They are freely available. And the third option is capillary water. When I say capillary water, so if I mix particular amount of moisture content to any soil, this water actually is not adsorbed, it is not freely available. It exists only because in between soil particles, a thin tube-like void is there, because of which in the atmosphere there is a pressure, below the soil there is a pressure. So because of the atmosphere pressure difference, from higher pressure from top to the atmosphere, water always wants to come to top. If you see this phenomenon usually in plants also, capillary action is the phenomenon because of which actually plants take water from ground. So if you see water, because of gravity everything should move from top to bottom. But if you observe in plants how they take the water from ground, usually water flows from bottom to top. This is because of capillary action happens. So this capillary action is just because the arrangement of sand or soil particles forming a connected air voids, which creates the pressure difference from atmosphere to the below the soil. So whatever little moisture content exists, that tries to move to top. So this capillary action water can evaporate at any time. If you further add little more water, that meniscus may break, and it can happen that it is a unstable water. So this plasticity character, is it because of the capillary water or adsorbed or free water? When you do this plasticity test, if you remember, we try to make a 3 mm of thread, we try to roll. The water content corresponding to which it will actually crumble is what we say that plasticity index. So when you are molding the soil in that condition, this capillary action or water related to capillary action could have been already disturbed. So definitely must not be that. And when you see the option B, free water, so whatever the free water is, as I have discussed previously, diffuse double layer. First layer is very strong, which is attached to the clay, and the second layer is what, which is very weak. This weak layer is what actually because of free water. So the adsorbed water which is attached to the clay is what actually changing the characteristics of the clays, which is nothing but the plasticity. Okay. For anything and everything we have discussed today, is there any other clarifications or do you have any other discussions you wanted to? Because in the next coming session, you have your submission deadline, right? I think 8th, 9th. your assignment 1 and 2. So once after deadline is over, in the coming Monday, we will be discussing the solutions for both assignment 1 and 2. In addition to that, we'll quickly discuss the third week summary and a few numericals. So till now, whatever the part we have discussed is completely soil. The real flavor of payment engineering and materials, so you will be starting with the third week, which is aggregates. So we will be studying all those things in detail from now. Till now, whatever we have studied is, as much as transportation is concerned, the required amount we have extracted from the soil mechanics. We haven't gone in depth with that because that is actually not required for us also. Okay. Is there any other questions or clarification? Because if there is nothing, then we will wind up the session. Yes. Okay. You have registered for that also. Then you might need to send a mail to NPTEL team. But otherwise, don't they have another live session like payment materials? We have two sessions on Monday and Tuesday. Otherwise, if you miss, they would be recording and sharing that recorded lecture. You might need to take that because okay, actually in NPTEL section on the left side where they are actually updating your week 1, week 2, week 3, below that there is one section they have added, problem solving section. So if you click there, actually they are giving all the recorded links and material. You can actually go and download from there. Okay. Those details SAR will be sharing with you. You don't need to worry. Okay. Starting few slides, which concepts do you want me to rewind, Dinesh? So I have starting with, so can you see my screen? This is a summary I have started with. Then, okay, this two till what? Till where you have missed? Okay, okay. So this we just discussed about the difference between the compaction curve of cohesive soil and also cohesionless soils. See, we have seen that half of the cohesionless soil curve is almost same as the compaction curve of the cohesive soils, but there is a little difference in the initial starting. So we have explained why it is different. So initially, when the entire sand is in the dry state, it has particular density. When I start adding the water, when I start adding the water, what happens is the little amount of moisture, whatever I am adding, so due to the capillary action, now all the sand aggregates try to come closer because of the water. Then whatever the connected airs between them will form a capillary action. Then always water wants to come to the top because the atmosphere pressure is higher. So water, whatever is at the bottom, due to the capillary action, it wants to suck to the top. So when it is trying to come to the top, what it does is it also tries to make the sand to move to top. So usually when do we say any material is higher dense material, if they all are completely settled compact. But here because of capillary action, all the sand is about to move to the top because water always try to move to the top. Because of that, what happens? Dry density decreases, 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 but it will not decrease forever. So there will be a condition where in between 4 to 5% of water content, usually there will be a least dry density. So beyond that, if you start adding the water, the whatever capillary tube or capillary air voids has formed, their meniscus will be broken. Now because you are adding more water. So once that is broken, so water you are adding now, sand will start settling slowly. So when it starts settling slowly, what happens? They try to come closer. Now the water we are adding, that will act as a lubricant. Slowly the density will increase. Beyond particular stage, if you still increase, now the dry density will decrease and it exactly behaves like a soil. So that is one of the concept we have. So this is basic shear strength we have discussed about cohesion and angle of internal friction, uh, why cohesive soils will have cohesion and sand will not have cohesion. And correspondingly, we have discussed about the direct shear test. So what is the purpose of direct shear test? If somebody has given a soil, if you want to determine the cohesion and angle of internal friction, we need to conduct some test so that it will give these two, because for any 2 to 3 multiple soils, if you have these parameters, you can actually tell what is the corresponding shear strength. So to determine this cohesion and angle of internal friction, the material has been subjected to a particular normal stress and try to apply a horizontal stress. At what horizontal stress this material will start fail? So the corresponding normal and horizontal stresses has been noted. So horizontal and normal stresses. So you can calculate the cohesion and angle of internal friction. So we have discussed there are some few disadvantages. For example, we are applying force here so that we are trying to make the specimen to fail at the half. So we are defining the failure plane. Usually this will not be the case. So we need to voluntarily allow the soil to fail in whatever the direction it wants to. So this test doesn't give that freedom to us. That's how we have come up with the triaxial test, where we give the confining pressure all around to the soil specimen and we apply the top deviatrix test. Then we allow the material to fail. Then based on that, actually this is what the equation in the initial slides we have discussed. If you want to know the normal stress on any plane, if you want to know the shear stress on any plane, here actually all these sigma 3, sigma d are normal stresses. So because they are normal stresses, instead of sigma x, sigma y, we have replaced with sigma 1 and sigma 3. And here we are not applying any horizontal stresses, that's why shear stress we have replaced as 0. So based on these two equations, we can still calculate the shear stress and shear stress if you wanted to calculate the shear stress. But if your criteria is to determine only cohesion and angle of internal friction, that also can be calculated. So the same triaxial test usually we do for one deviatrix test, let us say, but in field if you wanted to do repeatedly. So initial what happens, now you have a specimen, you applied particular load, then you remove the load. So now you give some rest to the material. Then what happens? So now the material has increased its length. Slowly it will try to recover. Again you try to apply the load. It will increase its deformation. It will come back. It might not go back to the initial stage because there will be some plastic deformation or unrecoverable deformation. Again you repeat this. That's why it is called repeated triaxial test. So after a particular number of loading times, what happens is this whatever this unrecovered or plastic strain, it keeps increasing. This is what we call accumulated plastic strain. And whatever remaining, this is called recoverable strain. So usually in solids, for example steel, modulus is stress by strain. There the strain is elastic strain, that means recoverable strain. So here we use only this recoverable strain and the applied load is deviatrix stress at the top. So deviatrix stress by this recoverable strain is what we call as resilient modulus. So this resilient modulus is usually used for the design of pavements. So in addition to that, we have discussed about CBR, DCP and plate load. So CBR is actually in the laboratory if you want to know the strength of the soil. So this is a soil specimen we take. We take a plunger of 50 mm dia. So we try to apply the load from the plunger to the soil. So when I am applying the load, this soil initially let us say it has height h. When I keep applying the load here, what happens? The height will be changing. How much is the height changing? That you can see here in dial gauge. So when the dial gauge reading reaches to 2.5 mm, we also will see what is the corresponding load I have applied. So we will note down that. And when the dial gauge reading reaches to 5 mm, what is the corresponding load we have applied? That also we will note. Because at 2.5 and 5 mm, what is the corresponding loads for a standard crust aggregate we already have. For our material, what is those loads we will calculate. So by taking the ratios, we can calculate the CBR at 2.5 mm and CBR at 5 mm. And we can actually represent it in terms of percentages. Okay. Okay, if nobody has any other doubts, I'll close the meet. Thank you.